You know that feeling, right? When you've played with magnets, you feel that strange, invisible push and pull. You can feel the force, but you can't see what's causing it. It almost feels like, well, like magic, but it's not. Today, we're going to pull back the curtain and uncover the physics behind one of nature's most amazing forces.
So, is it some kind of sorcery? Nope, not quite. The truth is actually way more interesting. What you're feeling is a fundamental force of the universe, and we're about to break down exactly how it all works.
Okay, so it all starts with one simple, unshakable rule. This rule governs every single magnet out there, from the little one on your refrigerator to the giant ones they use in science labs. And that rule is all about poles. See, every magnet has two ends, a north pole and a south pole. If you try to push two of the same kind together, north to north or south to south, they will fight you, pushing each other away with a surprising amount of strength. But flip one around, and those opposite poles, north and south, will snap together. This whole push and pull thing is our very first clue.
But why do they push and pull? I mean, what's carrying that force across the empty space between them?
Well, the answer lies in something completely invisible that surrounds every single magnet.
It's called the magnetic field. The best way to think about it is like an invisible bubble of influence that stretches out from the magnet. It's this field that's doing all the heavy lifting, putting a force on any other magnetic stuff that gets inside its zone. So, and this is the key part, the magnets themselves don't even have to touch for you to feel their power.
Now, you've probably noticed that the force isn't the same all around the magnet, right? If you try to pick up a paperclip with the side of a bar magnet, it's pretty weak. But if you use the end, it's much, much stronger. So what's going on? Why is the pole strongest right at the poles?
Well, it's all about concentration. That magnetic field isn't just a smooth, uniform bubble. It's actually made of what we call lines of force. And these lines are packed together most tightly right at the north and south poles. Wherever the lines are denser, the force is stronger. It's really that simple. But hang on, if these field lines are invisible, how can we be so sure they even exist? Well, this is where it gets really cool, because we can actually make them appear, using a couple of neat little tricks.
So first, to just see the pattern, you can sprinkle tiny iron filings around a magnet, and they will immediately snap into place, tracing the exact shape of those field lines. But that only shows us the shape, not the direction of the force. For that, we use compasses. If you place a bunch of small compasses around a magnet, you can see the flow. The needles will always point along the field lines, showing them streaming out from the North Pole and looping all the way back in to the South Pole.
Okay, so now that we get the field, let's talk about the magnets themselves. It turns out they basically come in two main flavors, the ones that are always on and the ones that just, pretend for a little while.
On one hand, you've got your permanent magnets, like the one holding up a drawing on your fridge. Their magnetism is just part of what they are. You can't switch it off. But on the other hand, we have induced or temporary magnets. These are things like a regular iron paperclip. They aren't magnetic on their own, but they become magnetic when they get close to another magnet's field.
And this is something you can see for yourself with a really simple experiment. We're going to use a permanent magnet to give a normal paperclip some temporary magnetic superpowers.
Here's how it works. You bring a permanent magnet close to an iron paperclip. The magnet's powerful field literally forces the paperclip to become a magnet itself. That's what we mean by induces magnetism. All of a sudden, that paperclip has its own north and south poles and its own little magnetic field. And you can prove it, because now that first paperclip is strong enough to attract and pick up a second paperclip.
But here's the catch. It's a temporary power. The second you pull that permanent magnet away, the magnetic field in the first paperclip just collapses. It loses its magnetism, and the second paperclip immediately falls. The magic is over.
So, in just a few minutes, we've kind of pulled back the curtain on this whole invisible force, turning what seems like magic into physics that we can actually understand. So let's do a quick recap. We've seen that magnets have north and south poles that either attract or repel. We've learned that this force is carried by an invisible magnetic field that's strongest at the poles. We even know how to make that field visible. And finally, we know that some magnets are permanent while others can just be temporarily magnetized. And all of that leaves us with one final massive thought. Our entire planet is a giant magnet with its own enormous magnetic field. We've seen how these fields work on a small scale with paperclips and iron filings. So, the question to leave you with is this. How does Earth's invisible planet-sized field shape our world and our lives every single day?